So I'm going to talk about one step that Raume was mentioning, which is basically detecting and characterizing macroorganisms in underwater images. So as it was said already, why do we need it? I mean, we need to monitor the biodiversity in oceans, in particular, for example, to check if there is invasive species appearing and checking the environmental conditions and maybe monitoring also some particular endangered species. And in ANERIS, I mean, part of it, everything was more exhaustively presented by the Raume, but we can observe it thanks to I would say mainly two pillars. One is the participatory observations, both with people getting some underwater images and sharing them also through the Minka platform, and also so some people going for this biomarathon on the coastal on different coast. And we also have underwater biooptics, for example, MUAS, which was mentioned, like these cabled observation points, which were developed in the context of the project, and that are going to provide some continuous flow of images, and some of them will be stored at some frequency to be defined. So this is a work from Oslo Met, and here they provide, if you're interested, some links so you can watch in live what is happening in these two observation points deployed so far. The presentation, as all presentation, will be put on Zenodo, so you will have access to all the links. So in this context, what we are in charge of as partner in the ANERIS project is this particular technology, which aims to help this detection and characterization. And then its purpose is really to get some input images, then work with the people developing ATOS that will talk next one. So Simon was supposed to come first, so you will discover what is ATOS after that, but basically it's a magical development to restore the quality of underwater imaging. And then what I'm going to explain you is how you can, from these images, detect specimens, maybe classify them, and then we will see the limitation of what is this classification and detection so far, and how we can add additional information based on segmentation, meaning that we could add some features, some measurements, such as the size estimation, the texture, and also getting more information about, for example, if there is a species next to each other and how many of them. Okay, so just as a quick reminder also, if you don't know about artificial intelligence, so it's a broad range. There have been a first workshop in ANERIS in December. Once again, everything is available on YouTube and on Zenodo to explain you more the basis of AI. So I will just go quickly through that. But basically, the classical artificial intelligence, it's when the developer or the person is basically setting up some rules, some program, human design rules, in order to process some input data, in order to get some output data. And then you have machine learning and deep learning, where the paradigm change a little bit, and basically you need to provide some input data, and what would be the expected output data in order to get what is called a model that can then be used to new data in order to produce the expected output data. Okay, so there is different flavors and of artificial intelligence, and one of them is setting up every rules by yourself. So basically designing as a computer scientist or image processing person, some rules to segment an image, meaning to get an image as this one, for example, it identify what could be species, doing some segmentation, and then from this segmentation, in order to get some classification at the end, what you could do is actually define some features. that you can express mathematically, but means something physically, like the texture of the fish, the size of the fish, the shape of the fish, this kind of information. And then you provide these features into something called a classifier, where you can then express this feature in a space that can be then simplified to two axes. And you should see species getting together in the same part of the space, and then you say this is the space of this species, for example, and then you affect this category to this particular segmentation based on the features that you have been computed. So this is a deep learning free approach. Just as a parenthesis, basically, if you want to add some parentheses, one way also to use deep learning here would be not to extract manually the features, but basically design the feature by deep learning. So I will not talk about that, but this is also a possibility. The thing is that for now, it happens that the deep learning is getting much more good results than the human-designed user detection and segmentation in most of the field, because deep learning is super good in these two tasks, in particular, detection, segmentation, and classification. But then there is an advantage of this approach, in particular in the fact that these features maybe, because they are humanly designed, they can help maybe certain observations to refine the taxonomic classification, and also when the deep learning model was not trained on one particular species, for example, and if there is any doubt. The other approach, which is like deep learning based, and is basically you train a model and you apply the model for detection and classification. So from one input image, you get directly some bounding boxes with the classification which was given to each of these fishes observed. The thing which has to be kept in mind, and that's a very important point to understand, is that this model has been trained on a specific database of images, so specific flavor of noise, of kind of content, of kind of background, and they are trained also to recognize specific list of species, and it's not infinite. They will just know how to recognize the species they were trained on, not a new one. The good thing is that it's super efficient if you use it on a similar data where it was trained on. And also what you could see, this little number is some kind of confidence score about the classification. So it's a good information also to know if the model is sure about what it's saying or not. Okay, so what do we do in ANERIS MAC is basically we take an hybrid approach, and in the sense that we use deep learning for the detection, we use deep learning for the segmentation, and then we extract some humanly designed features in order to give some humanly interpretable information about what has been done. So basically, we used this detection classification, giving us as an output some boxes and some proposal for species. Then we do some segmentation of the species, from which we extract some human design features, meaning that at the end of the full workflow, you get at the same time some information about what the model thinks the species was, but also some additional features. So maybe you can check if there is any doubt, or we could see what would be the different kind of application of this. In the workflow, we also use a first step, which is an image quality assessment. And this is basically some also human designed information that you can get from the images, giving you some information about the quality of the image, if it's constructed, if there is a lot of color, if it is a sharp image. And this could have a lot of applications. So for example, in particular in the context of this technology, is to assess if we need to go for a restoration model that will be presented next then from Simon. And Also, as I will tell you, the detection, I mean, we have, there is a lot of different models according to the kind of images you're using. So based on that, my hope is to automatize also the choice of the detection model, but it can also be used to monitor maybe the biooptics devices else. So for example, this is just a quick test, and we are still at the middle of the project, but some MUAS images, so just checking a few points. So here in this graph, what you see is the time and the quality metrics. So there is here 5 different quality metrics which are assessed. And you can see that at some point, one of them is basically dropping down. And if you look at the image, indeed something bad is happening, because maybe I don't know what's happening, but maybe there is some current, I don't know. But you can see the difference. So that could be super useful also maybe to monitor the quality of images getting. So then the next step after this quality estimation and potential denoising using ANERIS, which is not done on these images here, it's basically to detect where it could be some fishes. So here I get in the technology, you can choose between different models according to the kind of images. So for example, on the kind of species you are expecting. So there is more and more models, pre-trained models available. The one here, for example, is coming from OPSI, was developed by Enoch Martinez. And as you can see, every time you get some confidence. So here I didn't put any threshold just to show you. So sometimes because it was not trained exactly on this image, it thinks it's a kind of very big fish. Okay, but that's not a big deal because we have the features at the end to remove this one. And you can see, maybe you haven't seen this little fish here, but it was here indeed, it was a nice fish. Another model which is implemented in ANERIS math technology is a more generic train model, so it doesn't give the name of the fish, but yes, every model we have is pros and inconvenient. So I will explain you at the end of the talk also how you can train maybe your own model on your own particular part of the world that you are observing or the kind of images you have. But there is some of them already. So then the idea is to do some segmentation of this macroorganism. So for this, I use some foundational model, which is called segment anything. And it's restricted only on the bounding boxes that you have detected. This gives this kind of thing. And then you extract some features. So for now, there is a limited number of features. Once again, we are only at the middle of the project and we need to work more about the definition of the expectation for each use case we will be processing. But basically what is implemented so far are some parametric shape vectors. So basically the length of the fish, the aspect ratio of the fish, if it's like more compact or very elongated, this kind of information. Then there is also some non-parametric descriptors, which are like scale and rotation invariant, and which are basically different representation at different frequency, I would say, of the shape of a particular observation. So here you can see, for example, different coefficients at different orders, giving more or less information and more or less detailed information for one particular shape. And the last one, which is implemented so far, is some texture descriptors. For now, it's only in grayscale. But basically, this telling you if what you're observing is super uniform, if there is maybe some strokes, this kind of thing that you could observe. The nice thing with this feature is then you can look at what's happening on the, for example, the segmentation you have been doing. So what I'm going to show you now is some principal component analysis. So this is unsupervised, meaning you don't know what is the species. The color are given after that just to check where it was in this space of features. So if you use only parametric shape factors, so this is on a very limited amount of data. There is actually 3 true species and 1 false detection, but we will see that can be detected then. And if you use only this shape factors, the normal one, size, roundness, or this kind of information, you can see that most of them are very mixed. There is some ponds that can be isolated or not, but once again, you just gave the features and looks where the species are in the space, and you don't know nothing about the species to make this graph. If you use the shape, it looks like it's not so good also, apart from the fact that this different fish here in blue was separated well. If you use the texture itself, you can see that the false detection, which was this detected as some kind of miliobatis, which are actually some big stuff in the background, are very well isolated. And then if you mixed everything, you can see that most of the species, or few of them, are now well separated, apart one particular species, which is a little bit more elongated than the other one, which is mixed with the other one. But then, and that's what you do when you do, for example, classification in machine learning. Sorry, I forgot to say something, but the nice thing also is that when you use this kind of feature approaches and this reduction of features, like using this principal component analysis, you can actually give some explanation about what was the features the most important. For example, here it was mostly texture in order to that was discriminate more between every point, not knowing about the species, one again. Here it's very not a good score, 32% of variance, but once again, it's only on 7 images from one data point. And then you can use other tools like, for example, linear discriminant analysis. So this time it's supervised, meaning you're going to combine once again the features all together in order to get only 2 dimensions, as in the principal component analysis. But this time you do it such that you try to separate species. And here you can see that they are very nicely separated. And then what it means is that these features could be enough, for example, to differentiate this particular different species. Once again, it's just a demo what could be possible because we have a super imbalanced place in this particular example, meaning that we have only one example of Coris Julis in these images and one example of Dantex. Okay, so everything in the code is and the demo explanation are available on a GitLab, and you can use it. And okay, so if I just summarize, so basically the first step is to use a pre-trained model in order to detect, give some classification as a proposal to what you have been detecting, then do some segmentation, extract some features, and then play with the data and do whatever you want with the data using these features. So then comes the questions. So how do you train a model itself? And now it's super accessible for everyone to train is your own model. Basically, the 2 models I was mentioning, for example, even if there is more implemented, are based on YOLO V8, which is a specific architecture of deep learning for detection. So this box detection and classification of this box. And this is something now that you can access even from a Google Colab, for example, and if you have access on your own facility on computer infrastructure to Jupyter Observer. We'll try to put some in the context of the project in the EGI grid as well. And the nice thing with this model is that you don't really need a GPU to train it. It supports CPU training as well. And the big thing now is for you as a researcher to prepare your data set. So there is different tools. So for example, the company developing YOLO V8 provides some annotator to help you, which is called RoboFlow. and you can play with the API to automate it. Either you can also use your own data. You just need to export it, so you need to know a little bit about maybe data science, but just getting the right format. And basically, what you need is for each image, one file containing a list of bounding box and the classification you want to give to this bounding box. But you, what you need to know is that then you will need also to split your data, and you need training, testing, and validation. So just as a parenthesis, so what it means is that in order to use these deep learning models, compared to the fact of human design algorithm, the human time is more about the annotation, less than in the design of the algorithm itself. And in deep learning also, most of the time you need more images than in classical approaches. So the effort is a little bit shifted. So it's not magical, there is still some effort, and this would be in the preparation of the data. So I was saying that your job as researchers would be then to prepare this data. And what you have to understand is that when you are training a model, okay, you will provide this label data, meaning this bounding box and classification for each image. And you will train your model and watch how your model is getting good. And at some point, the error will be good enough. So you think that, okay, my model is good now. The only thing is that most of the time you are overfitting the data you have been training on. And if you test on another set of data, you will see that the error is getting up. So usually what you do, that's why you need some test data, you are getting some trade-off. So you will stop your model rather here. So constantly doing the training, testing and everything, and choosing the right parameters and the right models that will stop somewhere here. Even if you want to do better, you would train your data by doing some what is called cross-validation, meaning that getting the same big data set where you are label data, you will split them in this label data for training and test data, but you will shuffle the data every time in order to be sure that your model will be good in any new data as well. Then even better, and that's why you need a validation data. Usually you do this with an additional validation data set, and then you keep apart some data that the model will never have seen, just in order to assess the accuracy that you will get. And you can also apply a cross-validation for that. So that's basically where you will see if your model will be good enough to be applied on a new data, because most of the time you expect that the test will be always higher than the data on which it was trained, even for validation. Okay, so once you get this data set prepared, you can use some code provided. So with YOLO V8, I will actually add one simplified, so you can train your own data. And there is, for example, Jupyter Notebook, which are already available, I was saying, from YOLO V8 itself, that you can use on national local services, as I was saying. There is also, for example, EOSC providing some access to Jupyter server and a good architecture for free. And then it will be your work to assess if your model is good or not. And there is some tools. So for example, the confusion matrix that will tell you if you are good to recognize every species, or if there is any species where there is some confusion. Also regarding the detection box, there is some tools, metrics that you can check also, like the intersection of union of where the box should be and where it was detected, for example. Okay, so basically this is, yes, the first prototype of this technology, and once again there is still 2 years of development to come, and the thing is that it has to be adapted to, and it will be adapted to several questions. So that will be the thing to be prioritized together. when I say agile mode, the idea is really to be super iterative now that we have the basis in order to refine the needs of the different questions that we had. For example, there have been some questions about tracking, which should be very possible based on these features, just to say if we have a movie, for example, that it's the same fish we are looking at and not counting 100 times a fish, which was like just staying in front of the camera. And also the next step will be to add some calibration when it's possible and take advantage of the denoising that ANERIS is going to present you soon. With that, I would like to thank all the partners from ANERIS, but in particular these partners to which we have been interacting to do that. And once again, now the next step is really to define better the specific implementation of it toward this operational marine biology product that Jaume was talking about. So I will stop here.